Negative absolute temperature and heat flow in a spin system. A system consists of capital N spins 1/2, each having magnetic moment μ0, located in an external magnetic field B. The number of states of this system has already been calculated as a function of its total energy in problem 3.9. Make an approximate sketch showing the behavior of natural logarithm of omega as a function of E. Note that the lowest energy of the system is minus n mu 0b, highest energy is plus n mu 0b. The curve is symmetric about E is equal to 0. So here I have noted the result from problem 3.9 and problem 4.29 for ln omega as a function of energy and beta its derivative with respect to energy. So first of all, to answer part A, we have to make a few observations. So let's take a look at the symmetry of ln omega. So if I write ln omega of minus energy, you can see that it's going to be equal to capital N natural logarithm 2 capital N minus 1 over 2 n plus E prime. If it's minus energy, E prime is E over mu 0b. It's also minus E prime, so it's n minus E prime, natural logarithm of n minus E prime. And the next term will be minus 1 over 2 n plus E prime, natural logarithm of n plus E prime, which you can see is the same thing as natural logarithm of omega E. So the curve will be symmetric around an energy E is equal to 0. So let's find out what happens when the energy is 0 or E prime is 0, the same thing. That is natural logarithm of omega of 0. We will have capital N natural logarithm 2 capital N minus 1 over 2 capital N natural logarithm capital N minus 1 over 2 n natural logarithm n. So this will be equal to n ln 2n minus n ln n, which will be capital N natural logarithm of 2. So at 0 we have capital N natural logarithm of 2. And also I noticed that when the energy is 0, E is equal to 0 corresponds to beta is equal to the derivative of the natural logarithm omega with respect to energy. That is equal to 1 over 2 mu 0b natural logarithm capital N divided by capital N, which is natural logarithm of 1, which is 0. So E equals to 0 is an extremum point. So it is the maximum point actually. So if I look at the other extremes where the energy is minimum, so if on the other hand, if the energy is plus or minus capital N mu 0b, that is E prime is plus or minus capital N, I would have natural logarithm of omega E equals capital N ln 2n minus 1 over 2, and if it is plus n, this would be E prime is plus n minus n ln n minus n, and then here I will have minus 1 over 2 2n ln 2n. So this part will give me a 0 here. So this would give me capital N ln 2n minus n ln 2n, which is 0, because we have the same thing appearing here. And the same thing is true for ln omega of capital N mu 0b is equal to ln omega of minus capital N mu 0b due to symmetry. So it will be 0. Now I'm ready to sketch this. The ln omega function as a function of energy E has an extremum point at E is equal to 0 at capital N ln 2, and then it becomes 0 at minus capital N mu 0b. So when the energy is minus capital N mu 0b, it is 0. And when it is plus capital N mu 0b, it has to be symmetric. And when it is plus capital N mu 0b, it is also 0. So that's pretty much what it will look like. So part B, use the curve of part A to make an approximate sketch showing beta as a function of energy. Note that beta is equal to 0 for E is equal to 0. So let's take a look at beta as a function of energy. Well, if I look at the slope of ln omega with respect to energy, so for positive energies, I can see that. So if I take a point here, this is the slope of this curve. Or if I take a point here, this is the slope of this line here. So I can see that the slope is negative on this side and the slope is positive on this side. So basically I conclude for energy, for positive energies, positive energy values, del ln omega del E beta is negative. When energy is equal to 0, beta is equal to 0, that is maximum point. We already talked about that part. And when energy is negative, del ln omega del E is positive, so that would be the green line here. So if you plot, if you can sketch beta as a function of energy here, basically we see that beta is 0 at E is equal to 0. It is a negative for positive energies. So let's say that it is negative for positive energies, and then it's positive for negative energies. So it will look something like this. This is a qualitative sketch. And in part C, use the curve of part B to make an approximate sketch showing the absolute temperature as a function of E. What happens to T near E is equal to 0? What is the sign of T for positive and negative energies? Well, beta is related to absolute temperature. Beta is 1 over kT. So you can see that sine of beta is equal to sine of temperature. So if we have a positive beta, that means we have a positive temperature. If we have a negative beta, we have a negative temperature. When E is equal to 0, beta is equal to 0, that implies that we have a discontinuity in temperature. So qualitatively, we can plot temperature as a function of energy. So we have a negative beta or negative temperature for positive energies, and it has to give us a discontinuity at E is equal to 0. And we can see that it will be something like this. for E positive, temperature is negative, and for E negative, the temperature is positive because beta is positive. So we have discontinuity in T at E is equal to 0. And now, so let me separate these. This was part B, now this is part C. Let's talk about part D here. Since T suffers a discontinuity near E is equal to 0, it's more convenient to work in terms of beta. Show that del beta del E is always negative, hence prove that when two systems are placed in thermal contact, heat is always absorbed by the system with the larger value of beta. This is always true whether the absolute temperature is positive or negative. Okay, so I'm going to check the derivative of del ln omega del E. Beta is equal to del ln omega del E. It is from problem 4.29. It was 1 over 2 mu 0 b natural logarithm of capital N minus E prime divided by capital N plus E prime. So now I want to look at the slope of beta with respect to energy, which is the second derivative of omega with respect to energy. So I can rewrite beta as 1 over 2 mu 0 b natural logarithm of capital N minus E prime minus natural logarithm of capital N plus E prime. So let's work with this and calculate del beta del E. So del beta del E will be the derivative of beta with respect to E prime and E prime with respect to E. So I already know that E prime with respect to E was mu 0 b. So this is 1 over 2 mu 0 b. If I start taking the derivative with respect to E prime, I will obtain a minus 1 over capital N minus E prime and minus 1 over capital N plus E prime, and then this has to be multiplied with del E prime del E, which is E prime was given as E over mu 0 b, so it is 1 over mu 0 b. So here I obtain a 1 over mu 0 b. So if I continue with this, I will find a minus 1 over 2 mu 0 b squared 1 over capital N minus E prime plus 1 over capital N plus E prime. So this will give me minus 1 over 2 mu 0 b squared capital N plus E prime plus capital N minus E prime divided by capital N squared minus E prime squared. So the plus and minus E primes will cancel here. So I will find that the derivative will be minus 1 over 2 mu 0 b squared 2n divided by n square minus E square over mu 0 b square. So the 2's will cancel and my final answer will be then del beta del E is minus capital N divided by mu 0 b squared capital N squared minus E squared divided by mu 0 squared b squared, or if I distribute the mu 0 b squared here, I will obtain minus capital N mu 0 b squared minus e squared. So this will be the final answer for the slope of beta with respect to energy. So since the maximum value of E is capital N mu 0 b, del beta del E is always negative. So the slope has to be always negative. So if you look at the way I have plotted beta as a function of energy, here the slope is negative, and also on the other side with here I have a negative slope as well. So if I take a tangent at this point, I couldn't do it very well. So the tangent will give me a negative slope at that point as well. So the slope is always negative. Okay, so if I look at the situation when the change in beta is negative, so what does that mean? If the energy of system A is greater than the energy of system A prime, we know that this implies heat will be absorbed by the system A prime. Now if you look at the values of beta here, because del beta del E is negative, so you can see that with increasing energy you have a decreasing beta. So this implies that since we have del beta del E is negative, when the energy is increasing, beta is decreasing. So beta of A minus beta of A prime is less than 0. So this statement is equivalent to saying system A prime with larger beta value absorbs heat. So initially when we talk about a positive temperature situation, so here let's think about it. If temperature is positive, the larger beta, since beta is equal to 1 over kT, large beta corresponds to lower temperature. So it indeed implies that this will absorb heat. If the temperature is negative, however, we still have del beta del E negative. So basically that implies that also for negative temperature, if you have a larger beta, value also will be absorbing heat. So this concept of who is going to absorb the heat depends on the value of beta. The one with the larger beta value always absorbs the heat, whether the temperature is positive or negative. Now this negative temperature concept applies to the spin system of spins, because we only have spin degrees of freedom considered. So we are not considering the energy flow due to other degrees of freedom in the system. That is, we are considering the spins are locked at their position. So it's a manifestation of this assumption that we're seeing negative temperature for this system, possibility of a negative temperature for this system. Okay, so in summary, we looked at the behavior of the accessible number of accessible states, natural logarithm as a function of energy. We see that it has a positive slope for negative energies and negative slope for positive energies. The maximum is at E is equal to 0. So the entropy of the system is first increasing and then decreasing. So you can see that we have in this range, we have increasing entropy, and here we have decreasing entropy. So I shouldn't put the arrow here. So this is basically in this way. So because of this, change of entropy with energy is different, and when we add energy to the system, it's not necessarily true that the entropy will increase. We see a manifestation of this in the negative absolute temperature. So when we look at the beta, del ln omega del E, we see that the slope is always negative, as we have shown in part D, and there is an extremum point when E is equal to 0, beta is equal to 0. So that's where we have, so the curve has to go through 0, 0. And if we plot the corresponding 1 over kT, we see that for negative energies, temperature is positive. For positive energies, temperature is negative, and there's a discontinuity in temperature at 0 energy. So when we look at the derivative of beta with respect to energy, we find that it's always negative, and when delta beta is negative, that means we have heat absorbed by the system who has the larger beta value. Now for positive temperatures, this was already true. Larger beta value corresponds to smaller temperature or lower temperature, so it will absorb heat. But it's also true for negative temperature values. Larger beta system, because you can see the del beta del E is always negative. This is going to imply for the system when beta EA is greater than EA prime, beta A is less than beta A prime. So system with the lower energy will be absorbing the heat. So that's A prime will be absorbing heat, but A prime has the larger beta value.